So, have you ever really stopped to wonder, where does rain actually come from? And after it falls, where does it all go? Well, there's a whole fascinating science dedicated to answering exactly that. It's called hydrology, and we're about to break down its core concepts right now.
Here's a quick look at our roadmap for today. We'll kick things off with what hydrology is, then we'll trace the incredible journey of water through the hydrological cycle, see where it's all distributed across the globe, and then we'll connect it all with key concepts like the water budget. Okay, let's dive right in. First things first, let's tackle the most fundamental question. What exactly is hydrology?
You know, the name itself gives you a pretty big clue. Hydro means water, and lology means the study of. So putting it together, hydrology is the science of water. It's all about its occurrence, circulation, and distribution all over the Earth and in the atmosphere. It basically answers the big questions: where is the water, how is it moving, and where does it end up?
So why is this so important to study? Well, because its practical applications are literally all around us. For anyone in civil engineering, this is crucial stuff. We're talking about designing massive hydraulic structures like dams, managing water supplies for entire cities, creating irrigation systems for farming, generating clean energy through hydropower, and even figuring out how to control floods. It's a really big deal.
All right, now let's get to the very heart of this subject, the hydrological cycle. You probably know it by its more common name, the water cycle.
Think of this as the planet's engine for water. It is a completely endless circulation of water between the Earth and the atmosphere. Water evaporates from the ocean, it rises up to form clouds, it falls back to Earth as rain, and then it makes its way back to the ocean to start the whole thing over again. It's this constant, powerful, and unending cycle.
And here's a crucial point to remember. Throughout this entire journey, water is constantly changing its state. It moves between being a liquid, a solid like ice, and a gas in the form of water vapor. All three of these states are absolutely essential for the cycle to work.
So to really wrap our heads around this cycle, we need to break it down into its individual parts. Let's take a look at each process one step at a time.
So, the cycle kicks off with evaporation. This is a pretty simple process. When water gets heated up, mostly by the sun, it turns into vapor. And as you can imagine, the vast majority of this happens from huge bodies of water like oceans, lakes, and rivers.
So, once all that water vapor is up in the atmosphere, what happens next? Well, what goes up must come down, right? That's precipitation. As the water vapor cools, it condenses and falls back to the Earth's surface. And we know this as rain, snow, or hail.
But think about this. Does every single drop of rain actually hit the ground? Not quite. A lot of it gets caught on the leaves of trees and plants or on the roofs of buildings before it ever reaches the soil. This process is called interception, and that water might just evaporate right back into the atmosphere or slowly drip its way down to the ground.
As you can see right here, the canopy of the trees and the rooftops act almost like a shield, intercepting the rain and stopping it from immediately becoming runoff on the ground.
So, what about the water that does make it to the ground? Well, a good portion of it begins to soak into the earth. This process, where water on the surface enters the soil, is called infiltration. And this is exactly how the soil gets its moisture.
And you know, plants play a really key role in this cycle. They act like biological water pumps. They absorb water from the ground through their roots, and then they release it as water vapor into the atmosphere from tiny little pores in their leaves. This whole process is called transpiration.
And this shows that continuous journey perfectly. Water gets into the roots, travels up through the stem, and is then released from the leaves, right back into the atmosphere.
Now, infiltration gets the water into that top layer of soil, but the journey doesn't stop there. Percolation is what happens next. It's the deeper, downward movement of that water pulled by gravity through all the different layers of soil. And this is how our groundwater reserves eventually get replenished. Now, not all the water that hits the ground infiltrates it. The portion that flows over the land, making its way to streams and rivers, is what we call runoff. And this happens in two main ways. There's surface runoff, which flows over the land, and then there's subsurface runoff, which moves sideways just underneath the surface.
And you know those small puddles that form after a storm? The water that gets trapped in little dips on the land and can't run off? That's known as depression storage. That water will eventually either evaporate back into the air or finally infiltrate into the ground.
Okay, so now that we've broken down all the individual components of the cycle, let's zoom out and look at the big picture. Where is all the water on our planet, and how is it distributed?
The total volume of water on Earth is just enormous. We're talking approximately 1,386 million cubic kilometers. It's a number so large, it's pretty difficult to even imagine. But here's the truly staggering fact. Of all that water, a massive 97% is saline ocean water, which we can't use directly. The fresh water that we rely on for drinking and for agriculture makes up only 3%, just 3%. And the story doesn't even end there. If you look at that tiny 3% of fresh water, the vast majority of it, about 68.7%, is locked up as ice in glaciers and ice caps. Another 30% or so is groundwater. The surface water we actually see in rivers and lakes, it makes up a tiny, tiny fraction of that original 3%. So the amount of easily accessible fresh water is incredibly small.
And this really highlights a global challenge. Even in a country like India that receives a significant amount of rainfall, only a fraction of that water is actually capturable and usable for our needs. This makes managing it incredibly important.
This brings us to a really practical tool that hydrologists use, the water budget equation. You can essentially think of it as a way to do accounting, but for water in a specific area.
But before we can get to the equation, we need to understand a key term, the catchment area. You might also hear it called a watershed or a drainage basin. Simply put, it's the entire area of land where all the rainwater that falls drains into a single common point, like a river or a lake.
The basic principle here is as simple as your bank account. The amount of water coming in, the inflow, minus the amount of water going out, the outflow, equals the change in the amount of water that's being stored. It's a straightforward application of the principle of conservation of mass.
In hydrology, we express this simple principle with this famous equation. And the cool part is, it accounts for all of those components of the water cycle we just discussed.
So here's what each variable stands for. P is precipitation, R is runoff, E is evaporation, T is transpiration, G is groundwater flow, and that delta S symbol, that's just the overall change in storage. Now this is a very important formula from an exam perspective as it connects all the key processes.
This diagram really helps to visualize that balance. Precipitation is the primary inflow, while all these other processes like runoff, evaporation, and transpiration, they're all outflows, removing water from the system. Okay, to finish up, let's just touch on two more advanced concepts that add a little more nuance to our understanding: catchment leakage and residence time.
Now usually the boundary for surface water in a catchment matches the boundary for the groundwater deep beneath it. But sometimes they don't align perfectly. When this happens, groundwater from one catchment can actually leak and flow into a neighboring one. And this phenomenon is known as catchment leakage.
Now for residence time, which is a really interesting concept, it measures the average amount of time that a single water molecule spends in a particular part of the hydrological cycle, whether that's in the ocean, a river, or even in the atmosphere. The formula to calculate it is simple. Residence time equals the total volume of water in that reservoir divided by the average flow rate through it. And this leads to some amazing facts. For example, a water molecule can stay in the ocean for thousands of years because the volume is just so vast. But in a fast-flowing river, its residence time might only be a few days or weeks. So, to conclude, I want to leave you with this question to think about. Now that you understand these core principles, the hydrological cycle, the water budget, how can this science help us better manage the water resources right in your own local area? It's something to really consider. Thanks for watching.